Hello, everyone. Thank you very much for joining us today. Welcome to Campus Chem's very first virtual symposium, which is dedicated to CO2 reduction. My name is Kira Welter. I'm one of the editors of Campus Chem, and it's a great pleasure for me and for the whole editorial team to be able to host this event today. We will enjoy talks by three leading scientists in the field: Kartish Manthiram from the Massachusetts Institute of Technology in the US, Beatriz Roldan Cuenya from the Fritz-Haber Institute of the Max Planck Society in Germany, and Maria Escudero Escribano from the University of Copenhagen in Denmark. We were also very lucky to get Evan Stevens from Imperial College London in the UK to chair this event. He will be introducing the speakers and coordinating the Q&A sessions after each talk. Anna Nayas, the editor-in-chief of the European Journal of Organic Chemistry, is also with us today. She will be supporting us backstage and will try to reply to any general questions you may have, and which you can ask at any time using the chat function at the bottom of your screen. You can use the chat to communicate with each other, but of course also to ask questions to the speakers. Please try to start your questions with @Kartish, @Beatriz, or @Maria so that we can identify them more easily. This event is being brought to you by Chemistry Europe, an association of 16 chemical societies from 15 different countries. And the whole symposium is being recorded. You should receive a link to the recording in the next days so that you can watch it again in case you miss anything. We're really happy that so many of you registered. We received more than 1,000 registrations, which is amazing. So thank you very much for that. But well, we're all looking forward to the talk, so I don't want to keep you waiting any longer and would like to hand over to Evan, who will introduce the first speaker. Evan, thank you very much for being with us today.
Thank you very much. Okay, thank you very much for the introduction. So good afternoon and welcome to everybody. First, I'd like to thank Kira Welter and all her team at Campus Chem for inviting the speakers and bringing us all of us today, all 295 of us and rising. So it's really a colossal number of participants. They're all together today for the first ever Campus Chem webinar. So I'm really honored to be here, or virtually here, so to speak. So three really outstanding speakers on a really, really important topic, so CO2 electroreduction. So there's going to be 20 minutes for each talk and then 5 minutes of questions. So as Kira mentioned, please do write the questions in the chat. I'll try and remember to remind you to do so. Right throughout the each talk, do send your questions, and please remember who you'd like to address the questions to. So without further ado, I should introduce the first speaker. So that's Professor Kartish Manthiram. So Kartish is the Theodore T. Miller Career Development Chair and Assistant Professor in Chemical Engineering at Massachusetts Institute of Technology. So he received his bachelor's degree in chemical engineering from Stanford, and then did a PhD at Berkeley. So he's received countless teaching and research awards, most notably including the NSF Career Awards, the DOE Early Career Awards, American Institute of Chemical Engineers 35 under 35, and Forbes 30 under 30 in science. So his lab at MIT is focused on the molecular engineering of electrocatalysts for the synthesis of organic molecules, including pharmaceuticals, fuels, and commodity chemicals, including using renewable feedstocks, and that's what he's going to be talking about today. So without further ado, Kartish, please go ahead.
Awesome. Thank you, Ethan. Thank you, Kira, and the entire team at Campus Chem as well. So let me go ahead and share my screen. Excellent. All right. So I'm starting out with this image here because if one is asked where the carbon footprint is in this image, one would probably instinctively point towards the gasoline-powered vehicles or the electricity powering the lights. But it turns out that there is a CO2 footprint embedded in virtually every part of this image, that there is a carbon footprint behind the paper of the billboards, behind the patty of the McDonald's burger, behind the steel of the flagpoles, the cement of the buildings. The chemical and material world around us has an inescapable carbon footprint. And we need to find ways to avoid this carbon footprint, to somehow mitigate those emissions of CO2. So if we're trying to find new ways of synthesizing the chemical and material world around us, it's useful to frame this as a synthetic paradigm, that we can try to convert CO2, nitrogen, and water into diverse chemicals and materials that we use in our everyday lives. In this paradigm, CO2 would act as our source of carbon atoms, nitrogen would act as our source of nitrogen atoms, and water would act as our source of hydrogens and oxygens. And if we take these three feedstocks, we can try to move towards more complex products. So one would begin then with CO2, reduce that, making intermediates like CO or ethylene, take N2, react that with water, make it into ammonia, and then combine these three feedstocks together along with chemistries like oxygen atom transfer to make, for instance, acrylic acid or ethylene oxide, to make an amino acid or glycerol. These are at least a couple early stage examples that our group is interested in. Now, in this paradigm, what's useful is that all these feedstocks are distributed. CO2, nitrogen, and water can be found basically everywhere. And what we want to find then are routes which operate at benign conditions that are conducive to distributed manufacturing with these distributed feedstocks. So if we use electrical potential in the place of, say, temperature and pressure, this is something which is conducive to distributed manufacturing. So our goal is to combine not just CO2, nitrogen, and water, but to also use renewable electricity to force those transformations. So we'll focus in on one particular part here, which is the work that our group is doing on converting CO2 into CO. One can compare this to the conventional thermochemical method of doing this reaction, which would be to take methane, react that with water at greater than 700 degrees centigrade to produce CO and hydrogen. So this is the reaction which we refer to as steam methane reforming. This reaction has relatively harsh conditions since it's very endothermic. You have to go up to a high temperature. And in addition, because of this, one emits very large amounts of CO2 in order to generate that process heat. So we could envision instead an electrochemical process, one which could operate at ambient conditions, thereby overcoming the need for process heating. And this could operate at 25 degrees centigrade, a single atmosphere, and one could conceivably convert CO2 into CO. And this in turn would be a process which is not just carbon neutral, but carbon negative, because we're consuming CO2 to make a commercially important feedstock, CO, which goes into numerous products from there. Things like surfactants and basic solvents like methanol. There are diverse uses of CO industrially today, making it a very important chemical for us to figure out how to make sustainably. There are many different catalysts that one could conceivably use for this reaction. I show here a molecular catalyst, cobalt phthalocyanine. This catalyst we're especially interested in because it has a well-defined active site. This makes it something that's amenable to spectroscopic investigations. In turn, because there's a narrower population of metal sites, this also facilitates mechanistic understanding. So there are a lot of reasons for which we've gravitated towards here. There are, of course, many other catalysts like gold and silver and others, many of which are higher performing than this catalyst, but we've started here because of the fundamental insights that we can gain on this particular system. So I think it's useful to place this in context. Why cobalt as opposed to any other metal in this ligand framework? One can summarize this with this periodic table that I'm showing here, that if you go too far to the left on this periodic table, one tends to favor hydrogen evolution. This is associated with relatively strong CO binding, and hence these catalysts are not particularly effective for doing CO2 reduction. If you go too far to the right, these are catalysts that favor the generation of formic acid. This may in fact be mediated by plating of the metal out of the catalyst framework. And then there are catalysts in the middle here. One's based on, for instance, cobalt or nickel. These are catalysts which are relatively selective for converting CO2 into CO. And it turns out that the cobalt phthalocyanine is the most selective among these. There have been diverse efforts in the broader field to develop more advanced derivatives of cobalt phthalocyanine. I show here two examples, one using cyanide substitution and the other coordinating this macrocycle with a pyridine-based polymer. What we are doing in our work is to step back and to try to understand the cobalt phthalocyanine itself. There are many unanswered questions which can help to then further understand many of these more advanced efforts to make even more selective and active catalysts compared to the bare cobalt phthalocyanine alone. So we're starting here with just trying to better understand the mechanism of the cobalt phthalocyanine. So in our earliest work, what we recognized is that when we deposited the cobalt phthalocyanine catalyst and we looked at this electrode with a microscope, we could actually physically see crystals on this substrate, and that's shown here on the left-hand side. Each of these is a macroscopic aggregate of cobalt phthalocyanine. Cobalt phthalocyanine is quite liable to aggregate because it's a planar macrocycle. It stacks up like sheets of paper. The metal in one macrocycle coordinates the nitrogen in the next, and you get these diagonal stacking aggregates that ultimately end up making a crystal. And these are very typical deposition conditions in the broader literature. So it turns out that this sort of crystallization and aggregation, even though it may overall for the electrode lead to a good current density, that we're perhaps not getting maximum utilization of the catalyst. And so what we did then is simply dilute the catalyst and load it at a lower loading. And what we find is that at these lower loadings, these aggregates disappear. And this is something that's shown not just through the electron micrographs, but that one can also realize through kinetic analysis of these catalysts, that we can see now that these are in fact isolated sites. That's something that I'll show in just a few slides. So our physical picture now is that we have isolated sites, and that this is something which is relatively enabling for kinetic studies. So what we can do here first is see what the physical consequences of this lower loading of the catalyst if we optimize for turnover frequency instead of current density, which is the usual way in which these catalysts are probed. So here on the y-axis, I have turnover frequency for CO, and on the x-axis, I have catalyst loading. And you'll see that as I go to lower and lower loadings, the turnover frequency, which is the number of CO2s converted to CO per active site per second, that this increases dramatically. And so historically, the sorts of loadings that were used, which I showed a moment ago, around 10 to the minus 9 moles per centimeter squared, one would get a turnover frequency of, say, 1 to 10. And this is then the historic limit for a heterogenized catalyst, heterogenized molecular catalyst doing CO2 reduction in an aqueous environment. But if we further reduce the catalyst loading, you can actually get a dramatic enhancement in the turnover frequency, up to about 100 turnovers that we observe here. So it's important to emphasize, though, that this is something which comes at the expense of current density. So if you're trying to make the world's best electrolyzer, this insight by itself doesn't tell you much, other than that one is not maximally utilizing their catalyst at the typical loadings that are used. There are many innocent bystanders. Perhaps only 1 in 100 or 10 in 100 of the catalysts are actually being utilized. The rest have inaccessible active sites that make them be bystanders for this reaction. So one can look at this finding of turnover frequency at not just one potential shown here at minus 0.73 volts, but at a wider range of potentials. I think this is important just to get a sense of how this catalyst behaves as a function of potential. And you'll see relative to the highest turnover frequencies that have been previously reported in the literature, this sort of low loading, high dispersion limit does in fact lead to higher turnover frequencies at a wider range of potentials. So this is something which is very important for trying to kinetically probe this catalyst. One needs a catalyst which is not transport limited in order to understand the mechanism by which it conducts that reaction without convolution from transport. So that is what's enabling of this sort of dispersion method. And so we wanted to understand this more deeply. We can sketch out here first what we know from the literature, which is a very basic catalytic cycle through which COPC would convert CO2 into CO. And we have here a resting state. This is based on what's been asserted previously in the literature, that COPC with nothing bound to it should be the resting state in the system. That the probable intermediate here is this bound CO2 with following a proton coupled electron transfer. And what we really want to understand is whether this step is a concerted proton-electron transfer in which the proton and electron move together to the CO2, or whether this is a sequential proton-electron transfer one in which perhaps an electron transfers first and then a proton transfers afterwards. And this is, for us, a very important step to fundamentally resolve, because it impacts how one would look in the future to accelerate the very basic steps of this reaction. So it turns out that if one looks out into the existing literature for this question, one would find a divide, and that's part of why we focused in on this step. There are a handful of papers showing that this step should be pH independent. Those are the citations that I show here in orange. And then there are a set of papers which assert that this step is pH dependent. So these are divergent observations. In one case, if this is pH independent, we don't expect a proton to be transferred in the RDS. It should just be an electron transfer. In the other case, if it's pH dependent, we expect that this should involve a proton transfer in the rate determining step. So there are divergent expectations based on different parts of the literature, and we wanted to try to resolve that in our own work. So the typical way of looking at this problem is just to say that a rate of reaction is related to some reactant raised to some power n. And if I plot this on a log-log plot, log of rate versus log of substrate concentration, that the slope here is n, which is the order dependence. This is something of mechanistic significance. I could also, for instance, probe the Toffel slope on this catalyst. This is the rate, which has an exponential dependence on this factor m plus beta q, which is related to the number of electrons transferred before the RDS and during the RDS, m and q, as well as the transfer coefficient beta. This is then weighted by Faraday's constant and the potential that one's applying all over RT. And we can plot then the log of the rate versus the applied voltage. This linearizes the data. And the slope is the inverse of what we call the Toffel slope. So this is these are two pieces of mechanistic information that one would typically want to get from a catalyst of this sort. Now, what's usually assumed is that there are very simple kinetic limits, that the energetic changes are all small except in one rate determining step, and that there are no coverage effects as well. And what we really wanted to push back on here in this sense is that there can in fact be an interplay of multiple microkinetic steps. This is something which is routinely seen in thermocatalysis, where more complex mechanisms are sketched out and supported through the data, rather than just trying to push the system to a limit where a linear dependence is observed, which is often the case in electric catalysis. So this is just a realization that linearization of the data may be insufficient to pull out these more complex order dependencies. We wanted to more cohesively look at a more comprehensive set of kinetic data and use that to determine the mechanism at play. So the first sort of manifestation of this is to understand the mechanism as a function of catalyst loading. And this, I think, really helps to reinforce the importance of going to lower loading. So historically in the literature, shown in the black points here and in the red points on the far right-hand side, one has observed Toffel slopes that are relatively large for cobalt macrocycles. So for a perfluorinated cobalt phthalocyanine, as well as the closely related cobalt tetraphenyl porphyrin. And these Toffel slopes essentially leave one with very little mechanistic understanding. But if instead you use the lower loadings that we have shown in our work, shown here on the purple trace, one can actually obtain a Toffel slope which makes sense of 120 millivolts per decade. If one then goes to a higher loading, reflecting what's typically happening in many literature reports, one finds a Toffel slope of 230 millivolts per decade. So we can see in our own hands how loading can obscure the intrinsic Toffel slope in the system. One can systematically chart this out. Here, plotting the Toffel slope as a function of catalyst loading, and you'll see it starts very high on the right-hand side, and as you go to lower and lower loadings, it comes down and plateaus at around 120 millivolts per decade. So this is, for us, an important realization in terms of how to probe this system in the kinetic limit. There are many underlying questions here of the importance of Toffel slopes, and are there in fact cardinal values of the Toffel slope? This is something that our group has very recently put some work up on ChemArchive, and I encourage anyone who's interested to take a look at this. So what we looked at then is an effort that is working towards understanding the underlying mechanism of this catalyst in this low loading limit. So all the data that I'm showing from here is at the low loading limit, where we observe Toffel slopes that fall in the more reasonable range. So first, we did a kinetic isotope effect study here at a lower potential and a higher potential, and you'll see in both cases that this is a KIE of around 2 to 3. So this is reflective of the fact that there is a proton involved in the rate determining step in what we're showing here in particular. One can also look at the bicarbonate order dependence. This is an experiment that's been done in the literature, but here we're doing it at a wider range of potentials and bicarbonate concentrations. What you'll see here is that as I increase the bicarbonate concentration at a relatively low potential, that's shown here in purple at a low overpotential, that there's actually an inhibitory effect of bicarbonate. Increasing bicarbonate leads to lower turnover frequencies for CO. And as I increase the potential at the electrode, going to higher overpotentials, eventually bicarbonate has no impact on turnover frequency, and at much higher overpotentials, that it is in fact promoting of CO2 reduction. So we see that this is something that one can't easily linearize, that there is non-power law behavior and a deviation from a simple kinetic limit. So we can look at as well as the Toffel slope under a more diverse set of conditions. What I showed before was a very narrow range of bicarbonate concentrations. We can instead remove bicarbonate entirely or go to a much higher concentration of bicarbonate, and we see different Toffel slopes. So this is, it turns out that even something as apparently simple as a Toffel slope depends on bicarbonate concentration. So we can go anywhere from 86 millivolts per decade to 160 millivolts per decade. If we look at the CO2 order dependence, we see a slope which ranges from 0.7 to 1.03, depending on the potential. So at a lower overpotential, -1 volt versus SHE, we see an approximate first order dependence. But if we go to a higher overpotential, the CO2 order dependence drops. So these are a set of observations which one could not explain through simple linearization of the data. So we decided to systematically enumerate the different mechanistic possibilities. So first on the, I've sketched out here a direct step R1, which is a proton-coupled electron transfer to CO2 to get from COPC to this intermediate. There's a branch where there is first an electron transfer and then a proton transfer, and then another branch where there is a proton transfer and then an electron transfer. So this for us was what we refer to as a square scheme, in which all the different mechanistic possibilities for that single step that we're interested in have in fact been laid out. We can also implement bicarbonate poisoning, which we mechanistically see that as we increase the bicarbonate concentration, that we see apparent poisoning of the active site. So we saw that in certain regimes earlier. So we've implemented that using a simple electrosorption valency, that there's an equilibrium constant for bicarbonate poisoning, as well as a potential dependent poisoning term, that because bicarbonate is an anion, it is attracted to the electrode at smaller overpotentials, but as we increase the reductive overpotential, that bicarbonate is pushed away from the electrode surface. And so there is an electrostatic mechanism then that could govern whether or not bicarbonate is able to actually poison the catalyst. So we can take this and enumerate the steps. We allow in our mathematical formulation for there to be up to 2 RDS options in the kinetically relevant steps. All other steps are equilibrated. And we also allow for both water and bicarbonate to be proton donors. So in this system, we have collected 266 individual data points at 108 distinct conditions. We implement the models that we showed on the previous slide, and we validate them using what's known as the F-test, which allows us to quantify the goodness of fit. And so in doing this, we find that there are, in fact, 2 pathways through which this system is proceeding, that there is a certain regime in which a concerted proton-electron transfer occurs, and there is another regime in which an ET is followed by a PT. So there are 2 different mechanisms that are at play depending on the conditions at which the system operates. So we'll sketch out in more detail in just a moment the 2 regimes in which that occurs. We also see that bicarbonate poisoning is necessary. So mathematically, the system is allowed to choose whether or not bicarbonate poisoning is important. And the only way we can account for the data that we see is by having bicarbonate poisoning have relevant kinetic constants that in fact mean that bicarbonate poisoning is in fact occurring. So we can see now how our model fits this experimental data. The models are shown with lines and the experimental data with the discrete points that are plotted. And you'll see here that it agrees relatively well. In this plot, we can explain quite a bit by looking at the underlying model. And what we see here is that as we increase the bicarbonate concentration at a lower overpotential, that bicarbonate is poisoning. But as we go to a higher overpotential, that bicarbonate is electrostatically repulsed from the surface. And that in turn means that we no longer see a decrease in turnover frequency at higher bicarbonate concentrations, but an actual enhancement in turnover frequencies as the bicarbonate starts to act as a proton donor instead of a poison for the catalytic site. So we can extract this from the underlying model. We also see that many of these non-unity orders that we observed for CO2 order, that this is related to occupation of the COPC sites by a CO2 radical. And so as we go to higher CO2 partial pressures, we have greater occupation of the active sites. That in turn suppresses the apparent order in CO2, especially at higher overpotentials. We can reject other models. So if, for instance, we don't have bicarbonate poisoning, it's not possible to see the negative orders. You can see how the lines and the points disagree when there's no bicarbonate poisoning implemented. If there's no ET-PT pathway, in other words, a pathway in which an electron transfer precedes a proton transfer, we can no longer account for the non-unity orders in terms of the CO2 order dependence. What's very interesting here is that the dominant reaction kinetics change with operating condition. On the left-hand side, we've plotted out the fraction of sites that are blocked by bicarbonate. You'll see here that at more negative overpotential, so going to a larger overpotential, bicarbonate poisoning is disfavored. So one can electrostatically avoid it. And if you go to higher bicarbonate concentrations, bicarbonate poisoning is favored. And we can quantify this from the underlying model. We know the site balance at any given point in this wide phase space that we've tested. What's also interesting is that one can control whether a coupled proton-electron transfer happens or an electron transfer followed by a proton transfer happens. And so in this plot, you'll see that if you go to a more negative overpotential, the ET outcompetes the PT such that they are separated. So a higher overpotential facilitates electron transfer such that the two steps are no longer coupled. And this in turn has many consequences, that the conditions in which we typically test catalysts and understand their kinetics is often different from practical operation in an electrolyzer. But here we can actually bring the two together to say that even when we don't have integer orders appearing in our linearized data, that we can still deconvolute these more complex kinetic cases using the sort of methodology that we've shown here. So just to wrap up here, what I want to emphasize is that understanding of loading is critical for understanding turnover frequencies, that one needs to really pay attention to whether these systems are aggregated and hence are not reflecting kinetically limited activity. Fitting data over a wide range of testing conditions enables more complete mechanistic analysis. We see that the mechanism appears to shift depending on the regime in which we're operating, and that we can get a very fine understanding of how one can tune the system between being electron transfer, proton transfer dominant, or CPET dominant. And there are ways to also then, perhaps in the future, mitigate bicarbonate poisoning and enable lower overpotential operation with higher turnover frequencies in these sort of systems. So with that, I'd like to thank the students and postdocs who did this work. Joy Zheng especially worked on the kinetic analysis that I've shown here, which is some of our newer kinetic data. And Mingwei Zhu, one of our prior postdocs, did much of the earlier work on understanding aggregation effects. And with that, I'd be happy to take any questions.
So thank you, Kartish, for really pedagogical talk, actually. I think it's the insight you give is actually not only really important for CO2 reduction, but also for all kinds of electrochemical reactions. So, so we've got quite a few questions coming in, as I'd expect, actually. So let me just see. So there's one question from John One Park who's saying, what do you think are the major challenges that we need to overcome, other than developing catalysts to industrialize for mass production of the technology?
Yeah, I think there are many encouraging effects in the broader community on creating gas diffusion electrodes and higher current density electrolyzers for CO2 reduction. I think for someone like myself who started in this field around 2012 or 2013, when these sort of practical demonstrations were rarer and generally lower performing, it's very nice to see all that progress being made. Very little of that is in our own hands. There are other groups that are much better than we are at GDE design and electrolyzer design. So that's been good to see. Still, if one does the technical economics on those systems, it's clear that there's a ways to go in terms of getting, for instance, that capital equipment cost down to a point where one could operate, for instance, with intermittent renewables. I think that's sort of the gold standard, that if one were to use the capacity factor with renewables today, that would not be able to support the existing capital equipment costs. So I think there's a lot of efforts that are needed to continue to develop cheaper systems that can achieve the high current densities that are needed for converting CO2 to CO, as well as products like ethylene.
So, so I have another question from Pravin Ingole, who's asked, well, how about the stability of the catalyst? Does it get converted into cobalt nanoparticles during the CO2 electrolysis?
Yeah, so there's a set of studies out in the literature doing X-ray absorption spectroscopy on these catalysts. And what's very interesting is that while catalysts like cobalt phthalocyanine don't appear to decompose, there are others like tin phthalocyanine and related ones which will in fact plate out. So one has to pay very close attention, depending on the metal that's one's using, as to whether or not this kind of reductive plating out occurs or not. There are also other complexes which are prone to have the ligand become functionalized. So in phthalocyanine case, we don't believe that's occurring, but there are related systems, porphyrin-based systems, where it is believed, and there's good evidence to support the fact that the ligand itself can also undergo a reaction under these conditions.
So I have a very brief question myself, actually. So you mentioned the use of X-ray absorption spectroscopy. I know you're referring to other people in literature using it. So I guess there's a problem based on your literature data that if you can only really measure intrinsic activity at very low loading. So then that's probably too low loading to actually do in situ spectroscopy to see what the oxidation state or what the reaction intermediates are. Have you done any in situ spectroscopy? Do you know how you can get around these two effects?
Yeah, Ethan, you've honed in on the most important point in this entire system. And I would very much pose this as a challenge to the community, because we ourselves have not been able to resolve this. So the loadings that we're operating at, where the kinetics are very clean and observable and not transport deconvoluted, are loadings that are not amenable to the typical X-ray absorption spectroscopies and other methods that one would want to do in situ. And that's a critical challenge, right? This is, in my eyes, sort of like the pressure gap that exists in heterogeneous catalysis, or that once did, and that people have made concerted efforts over many decades to close. We have a similar challenge in this system where there's a loading gap, right? That higher loadings are needed for practical systems, for spectroscopic observations, but lower loadings lead to a kinetically observable system. So there's a gap here to be closed, and I think a great place for the community broadly to contribute.
Okay, thank you. So I have another question now from Yagyal Regmi from Manchester Metropolitan University. So he's asking, could you briefly explain how you're extracting the Tafel slopes? Are you using an algorithm to find the minimum slope, or are you just eyeballing the onset region of the polarization curve? And similarly, how do exchange currents change with catalyst loading?
Yeah, fantastic question. So if one looks at how Tafel slope analysis is usually done, it's exactly what is implied in the question, which is that one does just eyeball it. And that's historically what our group has done as well, right? We look for the linear region, we fit to it, and we say, okay, this looks all right. We ourselves have felt uncomfortable with doing this. And so in the last year or so, we've been working on developing an algorithm which enables automated analysis. So what the data that I'm shown in the slides here do not reflect that. It's data that we collected prior to that. But we have a toolkit which is now posted on ChemArchive which enables unbiased determination of the topple slope. So it's definitely something that I encourage looking at. We want to understand better the breadth of the utility of this, but so far we've only applied this to CO2 reduction in our own work.
Okay, great. And like I mentioned before, I'm sure it's very useful to all kinds of reactions. I think that often the topple slopes are overused in the literature. So it's, yeah.
Yes, there are many, many pitfalls with topple slopes, and so I really echo what you're saying, Ifan, that they're very dependent on conditions, and there are many non-idealities which push topple slopes around. So they should only really be taken as one piece of information in a broad context and not be over-interpreted. So I think that's part of what our sort of this new algorithmic toolkit that we've developed suggests, is that there may not be the sort of preference for cardinal topple slopes that we often say there is, right? Like when we're collecting kinetic data, we're often looking for a value of 40, 60, or 120. And if one looks broadly at the CO2 reduction literature, it appears that there may not really be a preference for cardinal topple slopes. There's very little peaking at the cardinal values if one looks at, say, 100 papers from the literature. So I completely agree with you, Ethan.
So there's, I think, time for one last question. So Hussein Al-Majed, again, I'm sorry for any mispronunciation. He says, a great talk. Has your group considered a proton transfer from neighboring nitrogens in this catalyst? And in other words, can protons from neighboring nitrogens react with the carbonate anion?
Yeah, we have in fact mechanistically sketched that out on a whiteboard. It is attractive to think about how the ligand itself can behave as a proton relay. And there's some efforts that are explicitly trying to do that in the broader community by using, for instance, hangman porphyrins and others that can behave as such. We have not yet been able to find direct evidence of this. So for us, remains a cartoon picture that's as of yet unproven. Another fantastic arena for spectroscopy to contribute in. But again, it's the same challenge that Ifan mentioned earlier, right? Which is that if you're at very low loadings where the catalyst population is uniformly engaged in catalysis without transport limitations, this becomes harder to observe. So if that gap can be closed, then this sort of question is one which I think is readily answerable.
Okay, so thank you very much, Kartish. We should all give you a virtual applause. It's been a really fascinating talk. So I think we should move on now to the next speaker. So it's Professor Beatriz Roldan Cuenya. So Beatriz is director of the Interface Science Department at the Fritz Haber Institute in Berlin, Germany. So that's a position she's held since 2017. So she began her academic career by completing her MSc in physics in Spain, and then did a PhD also in physics in Germany. So she went on to do a postdoc at the University of California in Santa Barbara. And in 2004, she joined the Department of Physics at the University of Central Florida as an assistant professor before becoming a full professor in 2012. So in 2013, Beatriz moved back to Germany and became a chair professor of solid-state physics at the Ruhr University of Bochum. And then she moved to the Fritz Haber Institute. So Beatriz is associate editor of ACS Catalysis and serves in the editorial board of the Journal of Catalysis, the Surface Science, and the Chemical Reviews journals. And is also in the advisory committee of the Office of Basic Energy Sciences of the US Department of Energy. She investigates well-defined catalysts with a whole arsenal of different characterization methods. And so today we're just going to be seeing a small snapshot of her very broad and exciting research profile. She's going to be talking operando structure composition, reactivity correlations during CO2 electroreduction. So without further ado, Beatriz, please go ahead.
Thank you very much for the introduction, for the invitation. I'm very happy to be able to share the work of my department today with every one of you. I think the most important thing I want to convey today is that to understand how a catalyst is working, you need to be able to follow how the structure is changing under reaction conditions. And I will give first a motivation of CO2 electroreduction, but we already had an excellent introduction, so I don't need to do a lot of work to motivate this. Then I will show you how we synthesize our catalyst, and I will go ahead and discuss some of the parameters that will affect the activity and the selectivity of our catalyst. For example, the particle size and composition, the shape, roughness, defects, or the oxidation state. So as it was mentioned before, we want to go from CO2, ideally using renewable energy, such as solar or wind energy, and we want to go from this to the production of high value products, for example, ethylene or ethanol. And the main idea will be that we want to control the selectivity of this catalyst, and we want to do it in a rational way. To do that, you can look at the earlier work from Hori, and you already find a problem. So when you're working with copper catalyst, just polycrystalline copper, if you change the potential, you see that the selectivity is changing. If you work at low over potential, you get mainly hydrogen. And if you go to the relevant potential, you can get the hydrocarbons, but these potentials are relatively high. So there is a need of lowering the over potential. And the beauty of this reaction is that if you change the catalyst structure and composition, and you also tune the electrolyte, you can modify the selectivity of your catalyst. So this is just an example from theoretical predictions, looking at what is needed. Why is copper so special? Why is the copper the only metal that is able to produce hydrocarbons and alcohols? If you look at the literature, there are some metals that make hydrogen, some metals that make formate, others make CO, but it's actually only copper, the one that makes significant amounts of hydrocarbons and alcohols. And this is attributed to the fact that copper has an optimum binding of absorbed hydrogen and absorbed CO. So we are going to try in my talk to make copper even better and to try to see what happens when I modify the structure and the composition of elements around copper. So first of all, there is a lot of literature already discussing beautifully many different parameters that affect the selectivity of CO2 electroreduction. For example, if you are working with surfaces or thin films, the roughness is very important. This has been shown to affect the activity. Also, if you have grain boundaries on these structures, if you have oxide species subsurface or at the surface of the catalyst, of course, the composition of your catalyst, and anything else that you have in the environment, the electrolyte is going to play a very important role. It could just serve as to reconstruct the surface, for example. It could also provide an electronic effect, and it has been shown that the pH of the electrolyte will also affect the selectivity. Even more, when you go to the nanoscale, you have nanoparticles, and you need to be considering that as a function of the particle size, you have specific sites at the surface, steps and kinks that are also going to affect the absorbate binding and also the binding of intermediates. If you play with the particle size and shape, you're going to affect all of this. So this is very complex. And to look at this and to try to get some understanding in my group, we started to work with model systems, but catalytically active. So we are synthesizing, in this case, nanoparticles based on colloidal chemistry. We can control the particle size and the interparticle distance. We can control the composition. And by doing this, we are going to be able to discuss structure reactivity correlations. In electrochemistry, it will be also interesting to be able to synthesize your catalyst also electrochemically. So for some of the studies that I will show you today, I'm going to demonstrate that you can synthesize very well-defined size and shape control, in this case, cubic structures, using electrochemical methods and using chlorine to stabilize the 100 facets. So to get started, what is the role of the particle size? I'm going to give you an example with zinc nanoparticles. So zinc is a metal that is able to produce carbon monoxide. And you can see here that with decreasing particle size, we can see an increase in the current density. This means an increase in the activity. So this is promising. So we can have a high activity for the high surface area material, in this case, the smallest zinc nanoparticles. The problem is the selectivity. If you look at the selectivity, we are making CO, that is the product that we want to make with zinc. But if you go to particle sizes below 3 nanometers, you see a decrease in the CO selectivity, and you see the increase in the hydrogen evolution reaction. This is, in this case, our parasitic reaction. We don't want to make hydrogen in this process. So something is happening here, and what we learn from comparison and from discussion with theorists is that on the surface of very small nanoparticles, in this case about below 3 nanometers or so, you have a large number of low coordinated sites that bind hydrogen very strongly. Then you are not at this optimum that we want to have. If you have these conditions, you are not able to produce CO. You favor always the hydrogen evolution reaction. And in the case of copper nanoparticles or gold nanoparticles, you see the same thing. You always favor hydrogen for the very small nanoparticles. But this is not enough. We also want to know what happens to our catalyst under reaction conditions. So we started with a zinc catalyst and it was oxidized. And if you go to the synchrotron and you look, for example, with X-ray absorption spectroscopy, in this case, X-ray absorption near edge structure spectroscopy, you can follow how the as-prepared sample looks like. And you see here the clear that the sample is oxidized. These are about 2 nanometer particles. And then under reaction conditions, you see significant reduction. But if you look carefully, and you look, for example, also at the extended X-ray absorption fine structure spectroscopy data, if you compare the as-prepared sample here, you see zinc-oxygen bonds, and under reaction conditions, even after a couple of hours at minus 1.1 volts with respect to RHE, you can still see the zinc-oxygen features here, the zinc-oxygen bonds. And in fact, if you look at the structure with more detail, this looks more like a hydroxide. So what we learned from this study is that, first of all, small nanoparticles are not good if you want to make CO. They will favor the production of hydrogen. And on top of that, the catalyst is not metallic under reaction conditions. Even under this reducing potential, it's actually an hydroxide. So if we now try to combine copper with zinc, we stay with large nanoparticles, in this case 5 nanometers. Here we know that we are not only going to be producing hydrogen, and we wanted to try to see if we can tune the selectivity by changing the, sorry, I think I was not sharing the entire screen, sorry. So we can change the selectivity by increasing the content of zinc. So here you see that with increasing zinc content, we can see a decrease in the current density, so a decrease in the activity. If we look at the composition, we can see a very interesting trend. So with increasing zinc content, we see that again we favor the production of CO, and this is here also hydrogen that we are producing. But if you are in a concentration here between 10 and 50% zinc in these copper zinc nanoparticles, we favor the production of methane. So what we learned is that for these small nanoparticles, there is a clear change in the selectivity when you change the content of zinc in these copper zinc nanoparticles. But even more, if you look as a function of time, here you can see the copper zinc nanoparticles. Initially, you are making methane, which is very interesting, but after 1 hour, we see a change in the selectivity. Here we see that we are making hydrogen, and in this case, the selectivity is changing after the first 2 hours or so. So what happens to our catalyst? It's not enough to know what happens to the pre-catalyst that we are making. We need to understand what caused this change in the selectivity. And to see that, we can do it under reaction conditions. So here we are at the synchrotron. Again, we are using X-ray absorption spectroscopy, and we are looking at our catalyst as prepared. We can look at both components, the zinc component and the copper component. And as prepared, our catalyst in red looks oxidized in zinc and in copper. But then under reaction conditions, you see the clear decomposition. This is here in blue is the copper oxide, and here also. So here this is zinc oxide, this is copper oxide, but it's not the degree, the rate of reduction of the zinc component and copper component is not the same. So if you look at the weight of the oxide here, within the first couple of minutes, the copper is completely reduced very quickly, while the zinc is reducing, the zinc oxide is reducing more slowly. So we think, we believe that this is affecting the selectivity, and because at the beginning we start having copper oxide in contact with zinc oxide, and then very quickly we have copper in contact with zinc oxide, and then at the end we're going to have copper interacting with zinc, so we make brass. To look at this in more detail, we can go and measure X-ray absorption spectroscopy. This is here the X-AFS data as a function of the time, reaction time. And to analyze this type of data and to get actual information about the radial distribution functions, that is very important to distinguish, for example, metallic copper from copper zinc, we are using neural networks. So you see here the data of a neural network is trained using simulations. We have created a database of X-AFS data created by using molecular dynamics. So we have several structures that we create, in this case thousands of structures that we use to train this neural network. And using this neural network, we can go from the X-AFS spectra to getting the entire radial distribution function of copper-oxygen bonds, for example, or copper-copper bonds, or copper-zinc. We did this here, and you can see that our prepared catalysts contain these copper-oxygen bonds, and then you also have metallic copper. I put here two references. This is a brass foil, and this is the partial radial distribution function of a copper foil. You can see that these peaks are different. You can distinguish very clearly. This is metallic copper, and this is here the copper zinc. So if you look as a function of time, as a function of the CO2 electroreduction time, during the first 20 minutes, you still have metallic copper. This is when you have copper interacting with zinc oxide. But once we reduce the zinc oxide, we see a very clear shift here in the radial distribution function that indicates that we're making brass. You can follow here the interatomic distances, and you can go from pure copper metallic as a function of the reaction time to the formation of brass. So our data help us, this in situ and operando spectroscopy data help us to understand the change in the selectivity. Brass makes CO and hydrogen. And if you have metallic copper in contact with zinc oxide, we can also make methane. So to go further, we wanted to look at the role of the particle shape, and there was some interesting previous studies for CO electroreduction showing that if you have 100 facets, you favor the production of ethylene. If you have other terminations, for example, 111, you can make ethylene and also methane. So we wanted to make on purpose 100 facets. And so we tried to do it electrochemically, and I show you here how we synthesize our structures. We are inside a liquid cell in a transmission electron microscope. This is our electrode, and what you see here changing in color here, this is copper nanoparticles. We have here a solution with that contains copper. We have chlorine that is going to help us to stabilize these 100 facets, and we are changing the potential, and you can see here that at some point we only get the cubic structures being stable. So this is for a certain potential how the synthesis looks like. All of this is copper, and then if you go to the right potential with the right concentration of chlorine, you only get cubic structures. So now I have synthesized in situ my catalyst. I have size control and shape control nanoparticles, and now I'm gonna go further and change the electrolyte. I don't want to grow anymore, so I remove this copper salt and I put my normal potassium bicarbonate electrolyte that I use in all my talk today for doing CO2 electroreduction. And then I'm going to apply the negative potential, and I'm going to see what happens to my initially beautiful cubes. So if you see here the data, you see first the mobility of the cubes. You see small particles being formed, so the cubes become unstable, they break up. We see dendrite formation, so you see mobility, breaking up of the cubes, the formation of smaller particles, and then these dendrites. And as I told you before, the selectivity is very strongly dependent on the structure of the catalyst. So what you make is only a pre-catalyst. It's actually very important to see what happens to this pre-catalyst under reaction conditions. And you see here how dynamic this is. How does this affect the selectivity? You see here the same cubes on a carbon paper support, and these are very large, in this case 600 nanometers or 200 nanometers, but there is a very clear size effect. In red is when we are producing CO2 electroreduction products, and in black is when we are making hydrogen. And so for the large nanoparticles, nanocubes, we make more CO2 electroreduction products than hydrogen. But if you go to smaller particle sizes, the cubes start to become more unstable, they break up, they form a lot of small particles, and they favor the production of hydrogen. So you see here the increase of the hydrogen production at the expense of the products that we want to make. So there is this structural instability is reflected on changes in the selectivity. So in the last part of my talk, I want to show you that we learn a lot about these 100 structures. They favor the production of hydrocarbons, and we decided to see, can we actually have these structures as a single crystal, and maybe we can pattern it, and maybe we are able also to stabilize a mix between metallic copper and copper plus. If you follow the literature, there has been indications that if you have a surface in which regions of metallic copper and copper plus, copper 2O, coexist under CO2 electroreduction conditions, maybe you favor the production of C2, C3 products. So we wanted to see this, and we use a single crystal to start to do this reaction, copper 100, and then we apply pulses. So the cathodic pulse is just the normal -1 volt with respect to RHE when we do the CO2 electroreduction. And the anodic pulse is going to be different, and we are going to go to certain anodic pulses in which we know that we are going to be oxidizing our surface. First of all, we want to know, are we really, from the CVs, you can already see that there are some peaks that correspond to the oxidation, but we want to see if we can assign this to copper 2O or copper O. And to do that, we have an electrochemical cell that is attached to our ultra-high vacuum system. So we can do the electrochemical reduction of CO2 here and then transfer in situ and use X-ray photoelectron spectroscopy to monitor the reaction. When you do that, we start first applying these pulses and we stop for 1 second at the anodic potential. You can see it here. And when we go to the potential where we know that we are oxidizing the surface, you can see here in the copper Auger data that you don't only have metallic copper, this is in green, but you also have a small amount of copper 2O, so between 16 and 20%. Now the question is, what happens if we go to -1 volt here only for 1 second? Does this copper plus remains at all? And the answer is yes. If you went initially and you had about 16 to 20% copper plus, you see reduction, of course, when you go to -1 volt, but it's not completely gone. You still see between 7 and 11% of copper plus coexisting with metallic copper. And this is going to be enough to make significant changes in our selectivity. But the pulses are not only doing that. So I'm going to show you here the selectivity for different pulse treatments. I'm going to ask you to look at this 0.6 volts. This is when we were having the production this is when we were having copper plus species. And I'm going to ask you to look at these two colors. In blue, this is ethylene, and in pink, this is ethanol. So if you don't apply any pulses, the copper 100 surface makes a lot of ethylene. And this remains when you apply the pulses, but when you apply the positive pulses, we first suppress the formation of hydrogen, this is here in black, and you increase the formation of ethanol very significantly. At the same time, if you follow the evolution of the CVs, you can see that they are also changing. So here, for example, this feature is typical of the 100 facets, and when we go further in the oxidative regime of the pulses, we can see that the formation of defects. So the structure is changing. So we can follow this. You can do atomic force microscopy. And when you run this reaction for 1 hour on a copper 100 surface, you see here the surface looks very flat. So not much changes. But if you apply the pulses, you see these massive reconstructions. Still, there is some order, but it's very, very rough. And actually, you see the formation of this type of pyramidal structures. If you run the reaction for 1 hour, applying the pulses, and then you just go to constant potential, the roughness somewhat remains, but here we don't have any copper plus left because we stay 1 hour again at this very negative potential. So this sample is going to have copper and copper plus roughness because the surface reconstructed, and this sample only has metallic copper and roughness. So if you look with differential electrochemical mass spectroscopy at these 3 samples, we are going to see very clear changes. So in red is the rough sample where we have also copper plus coexisting with metallic copper. We see here ethanol formation, and we see a very low onset potential for the ethanol formation. The blue curve here corresponds to the ethanol that we are making in the rough surface, but it's only metallic. And here, this is the surface where we didn't pulse. So ethanol is clearly suppressed. We see also a correlation with the amount of ethylene. So we favor the production of ethanol, it seems, at the expense of ethylene. And in all of the pulse treatments, we minimize the production of hydrogen. You can see here, when we look at -1 volt, you can see here the selectivity data again. This is when we run the reaction under potential static conditions at -1 volt. Here is when we apply the pulses, we see clearly the increase in the ethanol and the suppression of hydrogen. And now if we take this sample, which is rough, but we run the reaction at constant potential afterwards, we don't have any copper plus anymore, and we see that this affects very strongly the production of ethanol. So what we learn from this is that, yes, ethylene is favored when you have 100 facets, but if you have a defective surface and copper plus coexisting with metallic copper, you can increase the amount of ethanol. So going further, I would like to go to my summary. So I hope that I could give you some information about the role of important parameters in CO2 electroreduction, in particular the particle size, and how in this case, smaller is not better. So if you go to very small particles and you try to do CO2 electroreduction, you're going to produce hydrogen. I talk about the composition of the catalyst. And how is this important? Not just to look at the reactivity after 1 or 2 hours. In this case, our copper zinc catalyst was making methane for the first 2 hours or so. And then we see that the selectivity was changing, and we could explain why it was changing. The reason was that we start having the formation of brass, and on brass we make CO and hydrogen, not methane. And finally, I brought an idea of using pulse electrochemistry. In this case, we can do it to reconstruct the surface, and we can also do it to stabilize, for example, oxide species, in this case, copper plus species that are very difficult to stabilize when you are working at -1 volt. On top of that, you can also use it to regenerate your catalyst. If you, at some point under some conditions, you can get some contamination on the surface. The most important slide is the acknowledgement. So I'm very thankful to my research group. These are the ones that are doing all of this hard work. And of course, to our collaborators, many of the data that I show you here were acquired at a synchrotron, and there are excellent people working with us there and our sponsors. And I'm very happy to take questions.
Thank you for this really exciting talk, Beatriz. So we have a number of questions from the audience. Please do send more questions. We have a few minutes now for questions, but we have a lot already. So the first question I'd like to ask is from Van der Stram. Yes, do you have any idea how you can stabilize the cubes, especially since the motivation for cubes is the selectivity of the exposed 100 facets for ethylene?
So we have some experience. First of all, we need to make them large. So anything below 100 nanometers is very hard to stabilize. Second, we need to have chlorine in the electrolyte. So if you can deal with an electrolyte with a little bit of chlorine, then they are much more stable. We see that the cubes decompose when we lose the chlorine, and also when they become reduced, because initially they are not metallic copper, they are a mix of copper with oxygen and chlorine. So chlorine in the electrolyte plus trying to work not as low negative potential as -1 or -1 volt, but and also going to sizes larger than 100 nanometers. That's our experience.
So would you say that the presence of this kind of chlorine or also iodine in general is more of a kind of morphological effect as opposed to kind of co-absorption?
We have seen both, actually. We have seen, for example, iodine makes beautiful reconstructions on nanoparticles. But if you have iodine, you also see, for example, that you can stabilize copper plus species. And so, okay, you know, it's not one or the other. In many cases, we see that you see several effects. So when you get copper iodine as copper plus, and in the presence of iodine, copper plus is also more stable as copper 2O. We just published it recently in Angevante, so I think it's both.
I don't think I remember the paper. Sorry. So we have another question as well. Is it from Benjamin Sharif? He's asking, can you comment on the mechanism assisting the recrystallization and reorganization of the electrocatalyst, leading even to the formation of dendrites?
So what we see from the beginning is that we start losing the corners. So maybe I can, if later I can share the screen. But basically, we see first the corners go, and these corners give rise to the small nanoparticles. And then it seems that it's interesting that the dendrites are forming. We believe that it's probably following lines of electric field. But this is something that we need to look into more detail. The dendrites basically are starting to form from the seeds of the pieces of the cubes that we are breaking. So first we see from the cubes, we lose the corners, then the corners give rise to these small nanoparticles, and then we see these leftover copper atoms and small clusters. They basically start to serve as seed for the growth of the dendrites.
Okay, very interesting. How would you probe that if it's from electric fields, actually?
Yeah, that's a good question. So at the moment, there are certain possibilities of trying to do that by ex situ, so by trying to apply on purpose electric fields on different directions. In situ, in the TM, it would be much harder to do, but ex situ, you could in principle do it. We have not done it yet.
Okay, thank you. So we have another question from Victor Mugel, who says, great talk, thanks. Regarding the copper zinc nanoparticles, to what extent is the shape of the nanoparticles similar when varying the copper to zinc ratio?
So that's a very good question. When you use this inverse micelle encapsulation, normally you get spherical nanoparticles. especially if you have them on a weakly interacting support such as carbon. So in all cases, we did a very detailed atomic force microscopy investigations, and also we have data from cross-sectional transmission electron microscopy, where these are all spherical nanoparticles. And in all cases, we basically create a micellar nanoreactor, and then we load it with these different metals. So we ensure that we always get the 5 nanometer core, and then the only thing that we change for the same loading inside this core is how much copper versus zinc we load. So it's a very nice way to have same size, same shape, and only change the composition.
Okay, thank you. So the next question is from Marco Giovanni Antonio. He's asking, it's a more philosophical question. Do you think there's room for studies, not a more general question, I guess. Do you think there's room for studies not in operando conditions, for example, in ultra-high vacuum conditions or at low temperature, to address and provide answers to specific problems to CO2 reduction? If yes, could you give an example of an open question in the field that could be addressed by more fundamental studies?
I love the question because we are working on this, and I think this is, so I can give you an example. So we in the literature, the theorists at the moment are calculating perfect surfaces. So you have, for example, a perfect 100 surface. And in the theoretical model, you know where every atom is, and you don't have any contaminants around, and it's a perfect surface. So we tried to make a perfect surface. So we took this copper 100 single crystal, and we prepared it in ultra-high vacuum with sputter annealing. And then I did the reaction in my electrochemical cell that is attached to the UHV system. And so you don't have any exposure to air, and we know with STM how the surface exactly looks like. When you look at the selectivity of that perfect surface, atomically flat, you make mainly hydrogen and a little bit of CO. You don't make the hydrocarbons. So this brings, we are preparing a paper on that at the moment, but this brings a lot of questions because we can get from the same surface, once we start treating it badly, for example, we are doing an electropolishing treatment, the surface becomes rough, you get contaminants on the surface, then you start making hydrocarbons. So there is still a very big, large gap between what theorists can calculate and what experimentals can do. And if you're a surface scientist and you can work under these controlled conditions, you can help to close this gap. So at the moment, we are working on this and demonstrating that, in fact, a perfect, atomically flat, well-ordered copper single crystal doesn't make any significant amount of hydrocarbons. And everything that has been looked at before were either rough surfaces or electropolished. Even, you know, in the work from Horias, it was mainly not single crystals, always oriented foils. Another example is we are also working in chemistry in confinement. So we are working, putting two-dimensional materials in UHV on top of copper surface, trying to stabilize these oxide species, for example, copper oxide, because we know that this is important, but it's very hard to stabilize. So we are doing this in situ growth of two-dimensional materials to encapsulate an copper oxide surface, and then we are doing electrochemistry on that. So I believe there is a lot of room for fundamental surface science applied to electrochemistry combined.
That's certainly really interesting results, as you mentioned, because all these kind of theoretical calculations, they don't have space really for defects when they have a very small unit cell. So it probably means that they need to readjust their kind of assumptions in the model to try and explain their reactivity. I think that's a really nice thing, the kind of things you have in the Fritz Haber Institute for surface physics tools for understanding electrochemistry.
So I think looking at defects is key. So you said the right word. So we can, for example, for the person that was asking, we can do a scanning tunnel microscopy and do a spectroscopy on isolated defects, and then you can learn about the nature of this defect. And because you can combine the electrochemical cell with a UHV system, you can do the reactivity and play and change the density of these defects, for example, and see the selectivity is changing, and then try to go and do the spectroscopy. It's very hard to do any STM in situ after the reaction. We have some data, you don't get normally atomic resolution, so you have to match dirt, but you can still see the terrace and you can see major reconstructions. So we're also doing this in situ STM.
Okay, I really look forward to seeing those results in detail. So, okay, I think we're probably running out of time for questions. We should move on to the next speaker. So, but again, we'll give you a virtual applause. There's a lot of attendees. It's 470 now online, so it's really good.
Thank you.
Thank you very much, Beatrice.
I'm sorry, because at the beginning, I think I was not in full screen, right? I noticed too late.
I should have told you, actually. Sorry. Yeah. Sorry, I'm sorry about that as well. Thank you. Thank you very much. So for now, for the final, so certainly last but not least, we have a talk from Professor Maria Escudero Escribano from the University of Copenhagen. So she's currently assistant professor there and lead of the nanoelectrocatalysis group. And she graduated in chemical engineering from the University of Extremadura in the south of Spain and obtained a PhD in chemistry from the Autonomous University of Madrid, also in Spain, in 2011. Then she carried on postdoctoral research at the Technical University of Denmark, where I actually had the pleasure to work with her, and then in Stanford University also, before moving to University of Copenhagen in 2017. So she was awarded the highly prestigious William Young Investigator Grant in 2018. It's like a Danish equivalent of a ERC. And she's received numerous awards in recognition of her early career achievements, including the gold medal of the European Young Chemist Award, the Princess of Girona Scientific Research Award, and the Clara Imavo Award. So her group investigates tailored electrochemical interfaces for renewable energy conversion and electrosynthesis of green fuels and value-added chemicals. As you'll see in today's talk, she's a particularly strong proponent of electrochemical surface science. So without further ado, I'd like to ask Maria to go ahead.
Thank you, Ivan. Can you hear me? I hope you can hear me.
I can hear you, yes.
Okay, great. So I will...
I got word then that there was a problem with the connection, because I couldn't see you, but then now I'm happy I can see.
Okay, great.
Sorry.
Let me then share my screen. Yes. So I start. Thank you, Ivan, for the introduction, and it is a great honor to join this first ChemPhysChem symposium on CO2 reduction, and I want to thank, first of all, Kira and the rest of the organizers at the ChemPhysChem for inviting me along with Beatriz and Kartish. And it's a great honor to join you today. My name is Maria Escudero Escribano, and I am an assistant professor at the University of Copenhagen. And today my talk will be about understanding well-defined electrified interfaces for renewable energy conversion with a focus in CO2 reduction. And I don't need to give a motivation to the talk, because we had excellent motivation from the previous speakers. So we are interested in converting renewable resources and decarbonizing the economy. And we can convert renewable resources by coupling renewable energy to electrochemical devices. For instance, produce green fuels like hydrogen. We can use this hydrogen to produce green, clean electricity in fuel cells. And we can also be able to convert renewable resources into value-added chemicals. And that's what we are interested in doing in my research group by means of electrochemical reactions that take place in devices like this one. So in the case of CO2 reduction is particularly interesting because we are able to produce interesting fuels and hydrocarbons by converting CO2 and coupling with renewable electricity, being able to produce interesting chemicals. And all the reactions that take place in these electrochemical energy conversion devices occur at the interface between the electrode, which is going to be our catalyst, and the electrolyte. So this image illustrates something that Beatriz said before, the fact that when we are studying these electrochemical reactions, this electrochemical interface is extremely complex, and we need to take into account everything that happens both on our electrode surface and also on the electrolyte composition as the reaction proceeds. So we are interested in understanding this electrochemical interface with the best detail possible, being able to also tailor both the structure of our electrode surface and the composition of the electrolyte. And if we are able to tailor these interfaces at the atomic and molecular levels, then we will be able to tune the activity, ideally stability and selectivity towards the reactions that we are investigating. And for that, we can combine different methods. And an example, a really great example was what Beatriz showed in the previous talk. So what we really want is to be able to get an insight into the electrochemical interface as the reaction occurs, and for that we need in situ and operando methods, so we can combine electrochemical techniques with the other in situ spectroscopic and synchrotron studies in order to get this information on the electrode-electrolyte interface. And this is something that will be desirable if we really want to design and develop better catalysts for different electrocatalyst reactions. So we are involved in different electrocatalytic reactions for renewable energy conversion and sustainable processes, such as oxygen electrocatalysis. We are interested in both oxygen reduction and oxygen evolution, also on the reduction of CO2 and CO. And finally, we are very involved recently in the electrosynthesis processes, in particular synthesis of dimethyl carbonate from methanol and CO. And today I will focus on our work related to copper surfaces for CO2 and CO reduction. So definitely we don't need to motivate this, and I think that Beatriz already showed this figure. Copper is very special. And because it is out of the whole periodic table, it is the only monometallic catalyst that is able to go beyond CO. So we have certain metals that will produce mainly hydrogen. We have some of them, such as gold and silver, that are able to reduce CO2 to CO. And then some other metals are able to produce formic acid. But if we want to produce other fuels and hydrocarbons, we will have to use copper-based catalysts. And also, interestingly, depending on the structure of copper, we will have different selectivity towards different products. So what we want to understand is this electrochemical interface of copper with different electrolytes, and for gaining this understanding, model studies are very important. From the literature, and this is particularly from Ivan's work, we know that both the surface pre-treatment and the experimental conditions are very important and will affect the structure of our electrode. So the preparation of our catalysts, in the case of model studies using, for instance, single crystals, is crucial. We also know that the adsorption of electrolyte species and ion species will influence the structure and the CO and CO2 reduction. And also a recent work from Ib Korkendorf and Sebastian Horsch at DTU showed the influence of just the electrochemical cell. So just by, if you are in alkaline conditions and you work in a glass cell, there are certain contaminations that are going to affect your performance. And thus, for that reason, you need to avoid working in glass cell in the cases that you are working in alkaline conditions. So that was very inspiring for us. And then the work I'm going to show is focused on single crystalline copper, copper 111 and copper 110 in different electrolytes. In the case of alkaline electrolyte, we use a PFA cell, and all the work was done in the Hangis meniscus configuration. And what I'm going to present is a combination of cyclic voltammetry with the laser-induced temperature jump technique and molecular simulations. So for that, we have been collaborating with the Alicante group, Juan Feliu and Victor Clement in Alicante for the laser technique, and with Jan Rosmeister at my department at the University of Copenhagen for the theoretical calculations. And all the work I'm going to present has been done by Paula Sebastian, who is a postdoc in my group. So first, starting with alkaline, so Paula investigated both copper 111 and copper 100 in sodium hydroxide. And then here we can see both the effect of just the cycling potential range and the fact that, I mean, we can see from the CVs the fact that everything is very well ordered. And we can see the characteristic features both in copper 111 and copper 100 of the absorption of OH. So what we really want to understand, and that's why we decided to go for single crystalline surfaces, is how are the properties and the structure of these copper single crystals with the, in this case, with sodium hydroxide interface. And we want to gain information on the charge distribution and the structure of the solvent, because we know that that influences the electrocatalytic properties. So a parameter that is very related to the charge distribution and the solvent structure is the potential of zero charge. So can we estimate the potential of zero charge of these surfaces? It is something that hasn't been done for copper single crystals in sodium hydroxide. So we thought this was interesting to investigate, and Paula did a research stay in Alicante to use the laser-induced temperature technique. So I won't go into detail, and I'm not an expert in this technique, but in summary, what this does is to apply very short pulses of laser, like 5 nanoseconds, that gives rise to a sudden increase in the interfacial temperature, and that will shift the electropotential. So this potential shift will induce a disorder in the structure of the water depots, and thus decrease the dipolar contribution to the electropotential. So we have something like that. And then the change in potential when the temperature of the interface relax to room temperature, then the depots recover ordering. So this is a positive transition, and this is a negative transition. It recovers ordering, so you will have the ordered water molecules. And then these potential transients that are measured depend on so gives information on the orientation of the solvent molecules, the sign, and the relative intensity of the electric field. So this is going to give us information on the potential of zero charge. And in summary, this is something that Paula did using an electrochemical cell that, in order to work in these conditions, the electrolyte was confined in this space in the Teflon piece that they designed. And then they applied these transients for both copper 100 and copper 111. And we can see, so Paula did the experiments. Paula and Francisco Sarabia were the list of these experiments, and they did the experiments at different applied potentials. And as you can see, for both copper 100 and copper 111, there is a potential, a positive transient at positive potentials, and then the transient becomes negative. And just putting everything together, what this technique can give information about is about the thermal coefficients at different applied potentials. This thermal coefficient is related to the potential of maximum entropy, and this gives information about the potential of zero charge. So these are the CVs that I showed before, and this is the thermal coefficient. And what you can see here is that at some positive potentials, this coefficient is positive, and then at negative potentials is negative for both copper 111 and copper 00. And then this the potential at which this thermal coefficient is 0 will be the potential of zero charge. So interestingly, the potential of zero charge is related to the onset of OH absorption for both copper 100 and copper 111. And in summary, what this tell us is that actually this feature, which is a structure sensitivity, the OH absorption, is going to shift with the potential of zero charge. As you saw before, the potential of zero charge is very different from copper 111 and copper 100. And this is going to be very affected by the surface charge distribution. So this is just a very fundamental work that that gives information on the structure of our electrochemical interface, and it would be very interesting to continue investigating what happens in the presence of different anions, in the presence of different electrolyte, and also in the presence of CO. And this brings me to the second part of my talk, which is CO2 and CO reduction on copper, also single crystalline surfaces, and structure sensitivity and electrolyte effects. So as also Beatriz introduced, this CO reduction is structure sensitive, and the product selectivity will depend on the structure of the electrode and also on electrolyte effects. And given that CO is the key intermediate for the reduction of CO2 on copper, it's interesting also for some time of measurements easier to investigate CO reduction in order to gain an insight on the mechanism of this reaction. So as we saw before from Beatriz's group, it's really important to be able to control the structure of our catalyst, and the different structure will give will change the product selectivity. And this is something that we have seen both in recent and previous works by Mark Cooper and Hori regarding structure sensitivity, and also from theoretical calculations, and this is a recent work from Nuria Lopez's group. So we really want to understand what the interfacial properties are for CO reduction, and for that we use also single crystalline work in the hanging meniscus configuration. And then what I'm going to show, so what we were interested in is in studying the effect of having different conditions, potential range, and pH effect, and as well as electrolyte effect. So the questions that we want to answer is, what is the real surface state condition prior to CO reduction, and how CO is going to modify the properties of our copper single crystalline electrodes. So Paula has been doing these experiments in different, in phosphate buffer solution at different pHs, and this is just an example at pH 5. These are the cyclivoltammograms of this solution without CO, and this is in the presence of CO. So there are a few things that we can see from just these results. First, we see that when we have CO, the presence of CO, we see clearly differences in the structure sensitive features. So CO is modifying the structure of the interface. The surface, there are surface changes with applied potential. So when we go to, so this is just up and so top and down is just with different potential limits, and we know that the structure is changing with the applied potential. And also in red, we see what happens. We see that the surface passivation is happening. So there are many things going on, and all these things we really need to understand if we really want to, especially being able to explain this reaction and compare and bridge the gap between theory and experiments. So this is the same kind of experiments at pH 7, and what we see here, this is in the presence of CO, is the characteristic features of the anion absorption that are modified with CO. And what we also see is that this kind of so the structure is very different, and where CO is absorbed is very different from copper 111 and copper 100. So having these preliminary results, we were interested in pursuing like a more systematic study on both copper 111 and copper 100, and study this interface at the whole pH range. And this is something that Paula did. The work is, so we have the preprint published, and these are the CVs of copper 100 and copper 111, all in the presence of CO. So this shows the different cyclic voltammograms at all the pHs investigated. So these experiments, what showed is the CO displacement. So you have the typical phosphate adsorption features, and when you absorb, so phosphate is absorbed very strongly. When you absorb CO, you are able to displace displace the anions, the phosphate, and then absorb the CO. And this is what these features are telling you. So what we can see is that this is the pH has a strong effect, and we can also see that as the pH increases, the CO adsorption is shifting to more negative potentials, and we can also kind of see two different potential regions. So we can see it better here, and this is just the average between the anodic peak and the cathodic peak versus the pH. So we see how the pH influences this the CO adsorption features. We see that we can compare copper 111 and copper 100. The CO adsorption on copper 111 occurs at less negative potentials, and this is an indication that that on copper 111 the phosphate has a lower binding energy, and then that the CO adsorption is stronger on copper 100 than on copper 111. So this is something that we could more or less hypothesize from experiments, but we have combined this work with ab initio molecular simulations from Jan Gosmeiser's group, and I won't go into detail, but there so everything is very consistent between experiments and theory. The great thing about doing these very well-defined experiments is that we can really compare, because we are looking exactly at the same kind of electrochemical interface. And what we can conclude from both experimental and theoretical research is that the strength of phosphate anions on both copper 111 and copper 100 affects the potential range at which CO poisons the surface, and then the onset potentials at which CO adsorb is controlled by the properties of the interface. So this just highlights the fact that it is very important to do potential control experiments if we really want to understand and have a knowledge of the real surface state prior to the reaction that we are investigating. I don't know if we have time for that. I will go very, very quickly. So apart from working with single crystalline surfaces, Elena Plaza, who just finished a master's student in our group, and Paula Sebastian are also working on a method to deposit multimetallic catalysts in deep eutectic solvents. And this is very interesting because we can fabricate nanocatalysts with tunable morphology and composition, and in some cases they have very high surface area. So we are very excited about this project, and we are continuing on this. And just to conclude, what we really want, and that's why we are interested in going from model surfaces to more applied catalysts. We are interested in understanding the interfacial properties of well-defined copper interfaces. We think this is very important in order to design better catalysts for this reaction and for electrocatalytic reactions in general. Model studies are important for that. We of course need to combine all these and cyclic voltammetry and theoretical calculations with in situ and operando characterization techniques. And then it's very important to be able to tailor the interface at the atomic and molecular levels. And we have a lot of knowledge and also in situ interesting advanced techniques. And I think that combining everything this is a very exciting time for electrocatalysis. So this is my final take for the students that are joining us today. And finally, I want to thank all our collaborators. So all the theoretical calculations were done in Jan Rosmeiser's group. For the laser experiments, we have collaborating with Juan Feliu and Victor Clement. And I'm also privileged to collaborate with our chair, Ivan, and Beatriz through UNICIS-CAT. And the most important part, thank you to my group, this wonderful group of researchers that I'm privileged to work with on a daily basis, and especially to Paula, who has done most part of the work I've shown you today. Thank you.
Thank you very much for Maria for another really insightful talk. So as I mentioned before, please be forthcoming in the audience with your questions. So the first question we've got is actually from Nakiran Aromosi, who's asking, Maria, how do these single crystals pre-treated before measurements? Did you apply electrochemical pre-treatment or heat treatment?
Yes, this is a very good question, and so Paula spent some time to try to find a protocol. So it is all electropolishing, but very careful electropolishing in a stable potential region, until a stable CV is formed. And then we are also very happy to see that it is really compared to what you found, Ivan, with ultra high vacuum treatment. So the CVs look like they show these very nice characteristic features showing very good ordering. So with controlled electropolishing, we are able to do that. Paula is able to do that with her hand, which is also important, having good hands.
Yes, you have to remember of the single crystal experiments. I saw in some of the data you're showing, the voltammetric data, it looks like the anion absorption is more reversible in the presence of CO than the absence of CO. Why is that?
I don't have an answer for that, but definitely this is something that the CV shows. When you have CO present, you have very nice reversible peaks. What this is showing is the displacement of the anion. So it's with the CO, so it's like the CO adsorption indeed. So then CO is very reversible.
And so another, I have a quite brief question. So I know Hari noticed that when you're doing CO absorption, that it was really sensitive to temperature. So that in his group, they had to go to 0 degrees Celsius to do CO displacement. Did you observe this kind of sensitivity to temperature?
So as far as I am concerned, all the experiments have been done at room temperature, and all the results that I've shown are really reproducible.
Sure. Okay.
So this CO displacement, so CO is weakly adsorbed, but you can displace the anion.
And then another question is, what exactly is the role of the diputestic solvent in making nanoparticles porous?
Well, I mean, this this is I mean, you can control. So you can have very high porosity, but you can control the reaction conditions. I mean, the electrodeposition conditions and have different, very, very different morphologies. So it's not only having a deep, like an ionic liquid, and in particular a deep eutectic solvents, but also controlling what are the electrodeposition conditions. And I can tell you that, for instance, for this purpose, Paula and Elena have tried many different conditions, and actually the surface the surface area changed drastically.
And is it so when you see the you see, the shift in the potential zero charge that you see between copper 1, 0, 0, and copper 1 and 1? How well is that captured by the theoretical calculations?
This is something, as far as I am aware, this hasn't been done, and this is definitely something we want to do. I mean, collaborate with, for instance, the group of Jan, because I'm not sure that this has been studied theoretically.
Because it must have implications not only on absorption of anions, but also on the CO2 reduction intermediates.
Definitely.
Yeah.
So we are very excited because it is clearly so the OH absorption is clearly structure sensitive, and the potential of zero charge appears just at the onset of the OH. So that's very interesting and have implications for electrocatalysis.
I see. Okay, so I think we're pretty much done with questions. We've got a lot of really nice compliments in the chat for all the wonderful talks, and I'll second those compliments as well. It's been really, really amazing. I would like to give you a virtual applause, Maria. Thank you.
Thank you.
And then finally, before we should, I think Kira would like to give some closing remarks. But I'd like to thank you all for coming here today and listening to all these talks, and especially to all the speakers as well for really entertaining us and giving us a lot of insights. I'll pass that over to Kira. Thank you.
Thank you, Ivan, and thank you again to the three speakers, really, for the three fantastic talks. I would also like to thank my Wiley colleague, Anna, for the huge help behind the scenes. And of course, a very big thank you to all of you for joining us today and taking part in the discussion. There were some very good questions there. Our next virtual symposium is already around the corner. It will take place in a bit less than a month, on October 22nd at 4 p.m. Central European Time. The subject of the second symposium will be supramolecular chemistry. And we will again have an amazing lineup of speakers: Nathalie Busquert from Tulane University, Carson Bruns from the University of Colorado, and Steve Goldup from the University of Southampton. Nobel laureate Fraser Stoddart from Northwestern University has agreed to chair the event. And registration is already open, so please visit our homepage or keep an eye on our Twitter account, because we will be sharing the free registration link there very soon. Did I share my screen? No, I didn't.
No, it appears blank. Yeah.
Oh.
Sorry, I should have mentioned. Sorry.
Wait, let me try again. So can you see it now? Yes.
Still appears blank. At least on my computer, I can't see it.
Let me try again. I think there it is now, isn't it?
Yes, I can see it now.
Okay, great. So these are our speakers: Nathalie Busquert, Carson Bruns, and Steve Goldup. And well, please join us. It would be great to see many of you again there in October. I'm really looking forward to it. And so please take care, and hope to see you there again on the 22nd of October at 4 p.m. Central European Time.